We're ready to move into Chapter 3 to discuss organic molecules and functional groups. We've already been getting some of the concepts associated with this as we've been talking, and that's because functional groups are so integral to organic chemistry. I said this is one of the three biggies. This is so integral to organic chemistry that this is going to cut across all of the sections, the A, the B, and the C section of the course. And here we're going to get a little bit of a flavor. Question. When do we get to find out how we're doing on the quiz? With any luck, the quizzes will be by the end of the week. Typically, it's been about Thursday up on the rapid return, and you'll be able to see. And typically on quizzes, 10 is about an A, 8 or 9 is about a B, 6 or 7 is about a C range. All right, so the rapid return works very smoothly, by the way. This is something that's really been great. All right, so what's the functional group? Let's call a functional group an atom or a group of atoms and let's say with characteristic chemical and physical properties. In other words, functional groups impart to molecules properties like chemical reactivity that are very similar or related among molecules bearing the same functional group. Functional groups impart properties like intermolecular interactions that can give rise to boiling points, that have trends that are characteristic of molecules bearing particular functional groups. And I'll give you an example. We're going to trace through a lot of the common functional groups of organic chemistry over the next 3 lectures. So we started when I asked people to name organic chemicals. I think the first one that came up was alcohol. And so let me write out the structure of CH3, CH2, OH, more specifically ethanol. So ethanol is composed of 2 parts, if you would. It's composed of the CH3, CH2 part, the alkyl part. We would call this an alkyl group. I wouldn't describe an alkyl group as a functional group. In very old nomenclature, people used to refer to things as radicals in functional groups. That term radical has fallen out of usage for a good reason because it also means free radical molecule that has an unbound or unpaired electron. However, we'll refer to it as an alkyl group. The functional group is the OH, the hydroxy group. And the hydroxy group then is defining of all different alcohols, both alkyl alcohols and aromatic alcohols. And we'll learn what aromatic alcohols are in just a moment. So of course the alkyl group in ethanol is an ethyl group. And you can make different alcohols by using different alkyl groups. Let's take a moment to talk about the physical properties of ethanol, then we can talk about the chemical properties. So The physical properties of it is it has a relatively high boiling point. Now, relative is a tough term to compare, but you've already gotten this notion in general chemistry where you learn that water had a relatively high boiling point. And people said this is due to hydrogen bonding, the molecules stick together. It shouldn't be surprising that ethanol also participates in hydrogen bonding. It has OH groups, and the hydrogens on the electronegative oxygen can form a hydrogen bond, do form hydrogen bonds with other oxygen atoms in other molecules of ethanol, so they stick together. The boiling point of ethanol is 78 degrees Celsius. And usually the best way to figure if a boiling point is high or low, they told you water is a high boiling point. Fortunate for us, because otherwise we wouldn't be able to live on planet Earth. We wouldn't be here. That's say compared to methane. For a molecule that doesn't participate in many intermolecular interactions. For comparison on ethanol, let's just take ethane. Ethane is a gas. It's got an ethyl group in it. It's, of course, an ethyl group bound to a hydrogen instead of an OH group. Its boiling point is negative 89. Degrees Celsius. So ethane is very, very low boiling. If you want something that's the same size, so ethane, of course, is a gas. It's a component of natural gas. If you want something that's the same size, at roughly the same molecular weight as ethanol, we could take propane as a comparison molecule, CH3, CH2, CH3. Propane is also a gas. Propane boils at negative 42 degrees Celsius. So ethanol boils at way higher temperature because the hydroxy group is involved in hydrogen bonding interactions. You've always heard the term like dissolves like, right? Ethanol in many ways is like water. It's miscible with water in all proportions. Why is ethanol miscible in water, with water in all proportions? Well, the ethyl group isn't very much like water. It's greasy. But the hydroxy group is able to interact with the water through hydrogen bonding. And so even though you've got a greasy half to the molecule, you've got enough hydrogen bonding functionality for it to interact with water. What other sorts of chemical properties can we talk about with ethanol? We already talked about alcohols, and we said they're very weakly acidic. The OH group can be donated. Ethanol can act as a proton donor. The pKa is about 16. If you want to keep one number in your head, I said you can always just file away 17 as a generic number for alcohols. But the case of ethanol, it's just a hair more acidic. And just like water reacts with very strong bases, we've already seen some reactions. Write out one characteristic reaction that's very similar to the reactions we discussed, if not identical to the reactions we discussed when we discussed acid-base equilibria. If we take ethanol and we throw in sodium hydride, I'm going to start to write out some of the names of common compounds. We talked about the pKa of the hydrogen, and then we said hydride is a strong base because the pK of hydrogen is 35. You'd never get hydride alone. You'd never be able to get a bottle of just hydride. The negative charges would repel each other. As I've said before, literally the force of the explosion for the repulsion would be enough to blow up this lecture hall. So it's always paired with a counterion. Sodium hydride would be a common hydride source. If I mix them together, the sodium hydride reacts with ethanol. It actually fizzes quite vigorously, and you'll see the formation of hydrogen gas and sodium ethoxide. I'll write out the name of this salt. Let us call it of the base that forms sodium ethoxide. Thoughts or questions? Yes, good.
So you said that ethanol is useful in water because it can actually bond with water.
Uh-huh.
So how do you see where the water molecule is bond onto ethanol?
Ah, great question. Where does the water molecule bond on to the ethanol? So, we have two lone pairs, and we have a hydrogen. The lone pairs can hydrogen bond to other water molecules, which in turn are hydrogen bonded to other water molecules, and the hydroxy group can hydrogen bond to a lone pair on another water molecule. So these types of hydrogen bonding interactions are enough to drag the ethyl group into water. And in just a moment, I'll give you a little bit of a rough rule of thumb for figuring out when molecules are soluble in water. Well, what's powerful about an understanding of functional groups and properties is it gives you a way of making sense of all different molecules. The Chemical Abstract Service has just reported now 50 million reported molecules. Most of those molecules are organic molecules. And yet, after you've taken the A, B, and C course, you would be able to say something intelligent about every one of those organic molecules. You would be able to say, this molecule contains a hydroxyl group. It will react with a strong base like sodium hydride or sodium amide. This molecule contains an amide functional group. It's going to participate in hydrogen bonding properties. So that's the power of understanding different functional groups. So let's take another alcohol. Let's take CH3OH. CH3OH is methanol. I'll just point out it's another alcohol. And so it shouldn't surprise you that it has many similar properties. First of all, you can already look at it and see the anatomy. The alkyl group is a methyl group. It also has a hydroxy group. Methanol is sometimes referred to as wood alcohol because it was first produced from the destructive distillation of wood. Ethanol was first produced and continues to be produced by fermentation, and indeed this is one of the reasons why there's a hope for it as a fuel source that's renewable. Ethanol can also be produced from petroleum, which is a source of many organic starting materials, many organic feedstocks, and methanol can be as well. But methanol or ethanol? Methanol can be produced in ways, meaning not that are environmentally renewable. Yes, methanol can be produced in environmentally renewable ways. The destructive distillation of wood is actually a big mess. You basically heat wood and you get smoke and everything else, and you distill off the methanol. Methanol used to be used during bootlegging. During Prohibition, people would use it to strengthen their illicitly produced booze. Now, there's a problem with this. Methanol is toxic. It causes blindness. So it would make the booze stronger. It would make the hooch stronger, but it would also cause you to go blind. I guess they didn't care, which is kind of actually like modern-day drug dealers selling you all sorts of crap. All right. Anyway, what can we figure about methanol? Miscible with water shouldn't be any surprise. Miscible is just saying a fancy way of saying it mixes with water. It also shouldn't surprise us that once you know that ethanol reacts with sodium hydride, you'd know that methanol reacts, and you can even tell the name of the product. So methanol, CH3OH, everyone should be able to complete what I'm about to write here without my even having to draw it out. Reacts to form sodium methoxide, and even the name makes sense. If ethanol made ethoxide when you pulled off a proton, methanol makes methoxide. And also hydrogen gas, which would fizz out. What's that? The up arrow, yeah, you wouldn't normally see an organic chemist writing it because so few reactions we do generate gas. You'd see that more in freshman chemistry, but I've written that to remind us that the gas goes out. We've talked about equilibria, and a rule of thumb that I'd like to give you is if an equilibrium constant lies more than about 10 to the 10th, if it's more than about 10 to the 10th, about 10 orders of magnitude to the right, you'd say a reaction is essentially irreversible. This reaction is irreversible for two reasons. One is that the pKa difference is so big. Remember, the pK of hydrogen is 35, the pKa of an alcohol is 17, or we said 16 for ethanol, so that's a difference of the equilibrium constant is 10 to the 19th. But then also, since hydrogen is going out, Le Chatelier's principle says that reaction is just completely driven to the right. If you wrote an equilibrium arrow on this acid-base reaction, I think most people would sort of think it's very funny or laugh or consider it wrong. Okay. All right, let's take a look at some other alcohols, and there's a purpose to this because I don't want you to think that it's all the same, that all alcohols are just the same in their properties. And I want to show you the continuum as we vary the length of the alkyl group. So CH3, CH2, 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 OH. If we go up to 4 carbons, this alcohol is butanol, or more specifically, 1-butanol. Ethanol gets its name, ethane gets its name from ether, from air, actually, old name back to the 14th century. Butanol comes, well, butyric acid comes from butter. And so the name in butanol actually relates to butter. Butanol is soluble in water, but it's not miscible. It doesn't mix freely with water. It dissolves about 9 mils in 100 mils. Remember I said the alkyl group is greasy, the hydroxyl group is water-liking. Put specifically, the hydroxyl group is hydrophilic, it likes water. The alkyl group is hydrophobic. And by the time we get up to about 4 carbons, you see the effects of the alkyl group. So it's not miscible. We can't mix any amount with water. And I want to show you where this trend continues if we go on to another alcohol. And let's go and look at octanol. CH3, CH2, and I'm not going to write out the whole chain, so I'm going to say CH3, CH2 sub 7, meaning 7 CH2 groups, OH. So this compound is 1-octanol. What would you call the alkyl group in 1-octanol? If the alkane is octane, and so the alkyl group is an octyl group. Yeah, the alkyl group is an octyl group. And by the time we get to this long C8 chain, now we would really describe octanol as insoluble in water. By insoluble, I mean so little dissolves that you can almost say there's none. If you poured it in a well, I wouldn't drink the well water, but it certainly wouldn't be even 1 gram per milliliter. And so by the time we've gotten to 1-octanol, this molecule is more oil-like than water-like. And another place that we see a change in the properties, we saw that ethanol boiled so much higher than ethane. And yet by the time we're up to octanol, it still boils higher than octane, but not that much. So the boiling point of octanol, the boiling point of 1-octanol is, BP, is 194 degrees Celsius. If we compare it to octane, CH3 and then 6 CH2s, let's compare it. Actually, I think I've written down a comparison to nonane here, I think to make it the same size. So I think I've compared it to, just like we compared to propane, we'll compare it to a molecule that's essentially the same molecular weight, essentially the same size. If we compare it, it's 151 degrees. So we still have a higher boiling point, but it's just 40 degrees higher instead of well over 100 degrees higher, as we saw for the difference between, say, ethanol and propane. And like butanol, like ethanol, like methanol, it'll react with sodium hydride. So the hydroxyl group still imparts distinct chemical properties of reactivity, but obviously in the intermolecular interactions department, now we're getting the long chain alkyl group dominating in terms of effects, and it's just adding a little bit to the boiling point. It's not enough to drag it into water.
How would you pronounce the sodium oxide?
I would call it octyl oxide, sodium octyl oxide. That doesn't run off the tongue very well, does it? All right, let's start to discuss some hydrocarbons. I guess it would be octoxide, sodium octoxide, or more specifically, sodium 1-octoxide. Harsh. It's interesting, the small ones, sodium methoxide and sodium ethoxide, are widely used as reagents, because if you want a source of base, if you want a source of something that dissolves, or at least partially dissolves a little bit in organic solvents, often it's better to have an alkoxide than to have hydroxide. And so sodium ethoxide and sodium methoxide are widely used as bases in organic chemistry. In fact, the typical way I would use them, or Johnny or Buck would use them in an organic reaction, is to take some dry ethanol, and probably not to use sodium hydride, but actually to use sodium metal, and throw in a piece of sodium metal. This is a redox reaction, because the sodium is going from sodium 0 to sodium +1, and you're getting hydrogen going from OH, where the oxidation state is +1, to hydrogen gas, where it's 0. So typically you'd throw in sodium metal. Now here's another really interesting trend in reactivity. So if I throw sodium metal into water, it catches fire. There's so much hydroxyl group there, it just reacts very quickly. A little piece may not catch fire, but a big piece will catch fire. If I throw sodium into ethanol, there's enough grease there to attenuate it. It won't catch fire, it'll fizz around. And if I throw it into butanol, it'll go very slowly. So it's a nice way of generating a base. All right, let's start talking about hydrocarbons. And we'll take the complement to the methane, methyl, and ethyl, and octyl, and we'll start talking about alkanes. Alkanes are what we would call saturated hydrocarbons. They're saturated, meaning they have no double or triple bonds. Very early, as chemists began to study organic chemicals, before there were modern tools like nuclear magnetic resonance spectroscopy and infrared spectroscopy that allowed you to look at what parts are in the molecule to see signatures of functional groups that could immediately identify them. Chemists used various techniques to characterize, to figure out the properties of molecules, and one of them was hydrogenation. If you mix the organic molecule with a catalyst, like palladium on carbon, and you apply an atmosphere of hydrogen gas, does it take up the hydrogen gas? Does the volume of hydrogen gas diminish? An unsaturated molecule picks up hydrogen gas. A saturated molecule does not. And you've heard this term. Where have you heard the term saturated or unsaturated? Food, fats, exactly. And the fats, if they're from meats, have alkyl groups in them so that they don't pick up hydrogen. And if they are from plant sources, they have double bonds in them, so they do pick up hydrogen. And if you partially unsaturate the fat, if you take a liquid plant fat and hydrogenate it, then you get a hard fat that's like an animal fat that we call shortening or margarine. All right, so let's take a look at some alkanes, some saturated hydrocarbons. And I'll just show you a few. We've already seen a bunch. But let's see some more. So here's butane. The alkanes, as I said, are major components of petroleum. When you tap an oil well, there's usually natural gas on top that consists of methane and ethane and propane and butane, and then a whole bunch of fractions with pentane and various isomers of hexane and so forth. And typically what will happen in refining is they will distill to separate the higher boiling fractions that are useful for gasoline and kerosene and fuel oil from the lower boiling fractions. And then there are also processes called cracking that allow interconversion, catalytic cracking that allows interconversion of various alkanes. So if you want more gasoline and less fuel oil, you can control this in the process. Take a look at some others. An isomer of butane, and we've already got the concept of isomers. We've seen various isomers as we started to discuss structures in chapter 1. So I'll just write out the structure of 2-methylpropane. I've put a hyphen in writing on the blackboard so that it fits right under the molecule, but if you're writing it out on one line, you would just run the P right into the methyl, so it would be 2-methylpropane, all one word. This molecule is also called isobutane. We have a big legacy of common names in organic chemistry, and some of them just roll right off the tongue again and again. We'll take a look at one more alkane, and we'll take a look at a ring one. You've already seen ring structures in chapter 1, chapter 2 perhaps. So this molecule is a 6-carbon ring that's saturated, that has no double bonds. We call this molecule cyclohexane. Cyclohexane because it's a ring. It's not an isomer of hexane. Hexane has 6 carbons and 14 hydrogens. Cyclohexane has 6 carbons and 12 hydrogens. You've essentially taken away 2 hydrogens and closed the end. The one last thing I'll say about all of our alkanes is they are relatively inert. They don't react with many chemicals, and we'll pick up with this concept when we begin talking about alkenes